I have here an aluminum rod. It's just a standard piece of aluminum. It's about 7 feet tall, as you can see. What? Yes, I am. Okay, I'm going to put some rosin on this glove to make it sticky. And I'm going to use that stickiness to create some white noise. I'm going to squeeze this in the middle of the rod, forcing that to be a node. And I can make it sing. An ordinary rod can sing. Now, people, if you had special glasses that could see microscopically, what you would see is sound waves. Not sound waves going through air, but sound waves going through aluminum. And those sound waves are moving along this rod, left and right, and creating standing waves. Now again, if you could see microscopically, you'd see the biggest oscillations here, a little bit of oscillation there, no oscillation there, a little bit of oscillation there, and a lot of oscillation there. Okay? Now, you can also set up a transverse standing wave on this system by hitting it on the side with a hammer. Very different frequency. These are longitudinal standing waves going from an antinode to a node to an antinode. Now folks, if I squeeze it here instead of there, if I squeeze it here and do the same thing I did before, the pitch is going to change. Is it going to go higher or lower? Higher or lower? Talk to your neighbor, you're going to vote in just a moment.
I don't know.
Okay, let's vote. Those who say higher. Those who say lower. Okay, the lowers win. But this is physics. We can check. There's the first frequency. Higher. Now all of you that chose lower, I would ask, what were you thinking? And I'll tell you what you were thinking. You were thinking that this part of the rod got longer, and longer systems meant longer wavelengths, meant lower frequencies. That the long pipes in an organ are what give you the low notes. What you didn't notice was that this distance got shorter, and where I'm squeezing it has to be a node. This is free, so it has to be an antinode. The distance from node to antinode just cut in half. Now, the first time I rang it, I was squeezing in the middle, forcing that to be a node, and the ends were antinodes. How many footballs? One. This is the first case we've seen where we've had the endpoints the same, but it didn't go from node to node, it went from antinode to antinode. But I'm still starting with one football. And that makes all the difference. This is going to have a wavelength of twice the length of the rod, and that's going to be the first harmonic. Now when I squeeze it a quarter of the way down the rod, I'm forcing that point to be a node. This still is an antinode, and so the distance from antinode to node just cut in half. Now, if this is an antinode and this is a node, this must be an antinode, this must be a node, and this must be an antinode. This predicts that, well, two things. First of all, what frequency am I going to get compared to what I used to get? Twice, double. This is going to be F2. The wavelength's half as big, so the frequency is double. But the other thing that this predicts is that I'm squeezing it there, making a node, but there's another node right over here, a quarter from the other side. Let's test that. That's an interesting prediction that physics is making. This rod is ringing right there, and so if I grab it right there, it stops. But this predicts that it's not ringing right there, so if I grab it there, it keeps going. I can grab it there, it keeps going. I grab it anywhere else, and it stops, thank goodness. Okay? Now, what's going to happen? There it is.
They're all going to be hearing you. Oh, Craig.
Trust the force. Do you hear that?
Yeah.
How's your dog doing? Okay.